What's up, what's up, what's up? Welcome back. Today we're working on creating an allocator system that solves this problem in my code base. The problem being that there's a lot of error defers kicking around, and these error defers, if we're looking at like a coverage report here, are essentially like completely unrun, right? Basically, we have a lot of lines in our code base that we've literally never run in a like error critical path, right? So something goes wrong, chance of double free, pretty high. Chance of doing something stupid with memory, pretty high, and we've never run it, right? Because like we just haven't ever hit these cases, right? And so we've been kind of on this little bit of a saga to understand memory allocators, so that we can design a system where we can kind of just delete these guys, right? So the idea here is, say that we have some function that's gonna like alloc a thing and return. He takes an allocator and he returns the thing, right? So like he's gonna return a string or something, right? So this guy's gonna be like, maybe he does more than allocate a thing. He like allocates a thing and like does some stuff, right? So he says like, I've got something and I'm gonna do an allocate, like 10 U8s or something, right? And eventually I'm going to return that thing, but in between I'm going to be like, some failable action on X to populate it, right? Now, in the typical Zig world, you take in this allocator, you allocate the thing, and you do this, and you're like, wait a second, if this fails, this will go, this like won't get returned here, right? And our caller is supposed to go something like, alloc caller is going to be like, let's just say that he takes in the allocator as well for simplicity here. He's going to be like, he's going to say, X is alloc a thing with the allocator. And then later, he's going to free that memory, right? Like this. Now, do some stuff. Now, in this case, since he doesn't return to the caller, this never gets hit because he immediately bubbles up here, right? And like the memory is like gone. So what you would typically do is you'd be like, yo, let's say that we do this. On failure, just deinit the thing. Right? That's chill. But my problem here is that say, we do something else here, where maybe we refactor the code a little bit. And we say like, we actually want to return Y, and X is going to be some temporary thing. So we're going to like change this to like a constant defer, and this is now the thing we return. But oopsies, we left the X in here on the error defer. But because we never fucking run this code, then like, this will go completely unnoticed by us, right? And so the idea is that we want some system where we can basically just not do this, right? That would be ideal, right? And so like there's like a typical way that people like dodge this problem. There are these things called like arenas, right? And these exist in like Zig standard library, right? If we look up like arena allocator. So this thing like exists, and if you look at his behavior, essentially what he does is he acts kind of like he's got some. We're gonna pretend this is kind of like hand wavy. We're gonna pretend he has like an infinite amount of memory, right? What actually happens is there's like a page allocator that kind of like chunks in pages as they're needed. But we'll kind of pretend that he has an infinite amount, right? And there's like a pointer here, and as the pointer moves up, boom, 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 we get more allocations, right? So this is like our first allocation, second allocation, third allocation, chill, right? And then at some point we go, let's just nuke all of those allocations. And all we do to like delete those allocations is we like take the cursor, we just put it back to the beginning, right? So we just put the cursor back here. And so everything that came out of this pool is just like gone, right? And that's sweet, that works. Except there's no like concept of free in this world, which has like a huge performance advantage, right? In order to implement free, as we found out by going through like our allocator implementations in the past few days, like you need to track all of the memory that was freed, right? So an allocator that supports freeing is like has overhead. You just have to do more work. You have to write down all the places that you freed. You have to try to merge the free blocks back together. You have to like take those free blocks and try to return them to the system if you have 4K of contiguous free memory, right? All this stuff that you just kind of get to dodge if you use this simple allocation scheme. But where this scheme falls over is, say that we had some code in here and we're like, let's make something. We don't really, we have like some data that we want to parse, right? say we're doing some like JSON parsing, and in here we're like, we don't really know how long we're gonna like generate some stuff out of the data that comes in, and say like, maybe we won't say JSON parsing. Say the data, we're parsing something that's like, data comes in and data says like, I have 1,000 elements in him, and then he like writes down the elements, right? 1.0, 2.0, 3.0, right? Maybe this is a bad example. Maybe we'll say that the data comes in like chunks, right? So we have like, chunks of 100 elements over and over and over again. And we don't really know how many of those chunks there's going to be. And they can be like variable length, right? So we might do something like, we have some array list of like elements that we're going to spit out, right? And you might want to say, okay, we're just going to dynamically figure that out, right? So you might do something like this. Where you say like, we'll use an array list to build this stuff, and we'll kind of turn it into a slice at the very end, right? Now what happens here is you're gonna like do some sort of loop, right? And you're gonna say like x append, results of parse data, right? Or something. Let's maybe we're gonna do like while parse some data or something with some tracking index, right? We're just gonna pretend that there's like something that can advance, right? We're gonna do x append val. Cool. So the problem with this is that in an arena allocator, when you use this array list, you're gonna end up like reallocating memory over and over again. Because the way that like an array list works is like he'll start like really small, and then we'll go, there's like we didn't fit in here. Okay, so let's allocate like another thing over here that's like twice as big and free this. And then when that thing runs out, we'll delete that and we'll make a thing that's twice as big again, right? And it's like, that isn't friendly to this allocation scheme, because that means that every time we like reinitialize this thing, boom, out of like, we're just like losing memory, right? Our peak allocation or our peak amount of memory use is going to be like way too big. And this is solvable, right? You can solve this by not using an array list, right? And using something that like is like a linked list of chunks of equal size or something. You just append the next chunk of size every time. And then like you gotta argue that you could like reset the arena after this thing, and then like really like the overall cost isn't that bad, blah, blah, blah. But it's not that simple. Right? Because we are trying to solve a real problem in a real application. Don't forget, the problem here is our image editor. And our image editor has been written up until this point with the assumption that it can like use allocations as like scratch area, right? He's like, I'm going to, when I'm building a vertex buffer for things that I'm going to put on the GPU, I'm just going to like use an array list, fill it up, and then like figure it out later, right? While we could change all instances of those to do something more friendly, like guess the size up front, like reset arenas, all that, it would be nicer if like the integration could be simpler. And so that brings us kind of to where we are today, where it's like we want kind of like the benefit of the arena, that you have like a pool of memory that you've come from, and you can like delete that thing all at once. But we don't really necessarily want the like constant allocation thing, right? Maybe we do. In a lot of cases we probably do, but not in every case. Right? And so we need to have some sort of bailout. And I believe we've kind of proved this a little bit. I believe. Because we tried doing something here. I don't remember. Let's see if it works. We like hooked up an arena allocator to our GUI framework in some way, and we found like memory usage explode. I don't really remember what the context was of that. I think we probably undid that change, so we're not going to see it. But basically we saw that something that should take like maybe like a couple megs of memory, it takes like 20 megs or something. Like just like it's like insane levels of bloat. And I think it's because we were trying to, right. The reason for that was because we had some things that are like kind of like sub lifetimes of other things. So we kind of had, I think the thing we tried was we kind of have like our application, and our application will spawn like a GUI, right? And our GUI will spawn like as part of the GUI, we have like a sidebar. And as part of that sidebar, we're going to have like a label, right? This is kind of like, some sort of like object hierarchy, right? And this label wants to do some sort of like stashing of stuff or something like that. I can't really remember the details, but there's some sort of like compare that like the text that we have right now, if it's changed from the text we had before, then we have to like regenerate some like GPU buffers, reallocate some memory, and then we have to like remember that thing that came in and write it down for later, right? So this guy's constantly allocating text and freeing him. This guy is kind of constantly like resetting himself. Like all of the widgets that come out of that sidebar, or sorry, this section down here, the object properties view, these guys get changed, like regenerated every time I switch objects. Because like the widgets that are shown here are like dynamically injected, right? So sometimes we want to kind of like delete this whole section of the tree just to regenerate the sidebar so that like, you know, I don't know. So if we don't want to like free every widget individually and we want like an arena here, we kind of want like sub arenas in some way or something. There's something there. And so like what I'm kind of thinking, okay, let's like break down our constraints. Our constraints are array lists are used heavily in our code. Already, right? Set, what is it? Line break. We have some areas of the code expect to be able to like, you know, hold some memory for unknown periods of time. Example, like, write down the last thing you saw, type shit. And then we also say that like some whole area, like some areas of code want to be de-initted as a block based on some action. We'll say that this is the example of sidebar regenerates widgets on object selection. Okay, so with these constraints in mind, there's something about this arena is very nice, right? The idea that we could make the sidebar, we could try to like make it so that everything in the sidebar comes from like a pool of memory. But that pool of memory has to support the idea that this label is going to occasionally delete stuff, right? And so what I'm thinking right now, current idea. I guess we should also write down like, okay, current constraints, like noticed constraints, which means this means arenas are not too friendly here. Okay, essentially a tree of arenas, somewhat, yes. Okay. What we know based off of our current like investigation, we know that arenas and general purpose allocators both pull from page, like pull one, like in units of one or more pages. So like 4096 plus blocks. We know that general purpose allocators are more expensive, than arenas, with like varying trade-offs, right? So we, you know, a thread safe general purpose allocator will be more expensive than a non-thread safe one that you know, support like is like if you try to reduce fragmentation, you're going to trade that for like CPU effort to like keep track of stuff and not fragment and stuff like that, right? So varying cost for these things, but they are more expensive than arenas. But given these, you know, these two very like simple pieces of information, my current idea is we have like some sort of like top level page allocator. Okay. And this top level page allocator will spawn kind of like, we'll make like a tree of these, you know, sub page allocator that has like another sub page allocator. So this could be like GUI and this could be like sidebar, right? Then within each of these things, we're gonna have like a arena or bump allocator, as well as a general purpose allocator. And when we, instead of resetting the arena like you normally would, instead of just like taking the cursor and moving it back like this, instead, I think we just nuke the page allocator. So I think that we write down as part of our page allocator like how what pages have we allocated, and then we can just oopsies. Then we can just nuke all of the pages, reset our general purpose, reset our arena allocator, and then it's kind of like the same thing that the arena gave us, but like a little bit more complex. Or like a little bit more cost, I guess. Instead of just moving the cursor back, you're actually like unmapping pages. But I think that that gives us like something kind of nice. So that's the current idea. That's the current idea. We'll see where it ends up. Um, but that's kind of like the thing I want, because the reason that we have to do it this way again is because there are places in the code base that we need to support freeing from, and so they can just choose to use this guy or they can choose to use this guy, and it's possible that like maybe we kind of like nest it like this, maybe not, right? It's like maybe the general purpose allocator pulls from the arena, maybe, and then we have to think a little bit about like if these guys start like getting spun up a lot, if we start like trying to do this a lot, we might have some problems there, because like at the minimum, the arena allocator and the general purpose allocator are going to be mapping like at the minimum 1 page each, right? So there might be some wasted space there that we have to think about. But what I think like this is kind of the idea for now. We have like the ability to split off sub page allocators, and each of them will have these things. So each page alloc has this stuff. All right. All right. That's the idea. That's the idea. And so I guess after 16 minutes of explanation, we can write some code. Yeah. So maybe we start by making like some sort of little playground where we can kind of like experiment with the idea. So let's try to like mimic the behavior of our GUI framework a little bit here, right? So we're gonna have like some sort of like top level thing. You know, I don't know. Who knows? This guy is going to create some sort of like root tree object, I guess. Right? We're gonna have like something along the lines of like root. And maybe it's like something like this. Then we're gonna have like, maybe we call this like full app alloc. You know, something that is expected to live for like the lifetime of the application, I guess. And then we kind of say, hey, as like, you know, maybe we want like sidebar alloc to be something that's like, you know, split off from this guy, right? Split is maybe the wrong word. Maybe like make sub alloc. Sure, right? I guess we're gonna have to say later, you know, we're gonna deinit this whole thing. And we do not want to have to deinit this thing, right? We don't want to have to do that, because we want that to come for free from here. The only thing we care about here is the ability to reset him on some event, right? So we're gonna have some sort of event loop, and we're gonna say like event equals wait for event, right? And then we're gonna be like if event triggers, I don't know, change or something, we're gonna be like sidebar alloc reset and like regenerate sidebar, right? I guess it's gonna be something like this. This is kind of how it feels like it should make sense here. Okay. So I guess it's more just like generate sidebar here. Yeah. Okay, cool. That feels kind of like something. Feels like something. So now I guess we just have to make the players in this game. So let's, I guess we have to think a little bit about who like who's responsible for what, I guess, and also like in which cases we are going to pull for, sorry, in which cases I got lost. Oh yeah, which cases we're going to pull from like the standard library versus where we're going to roll our own thing. So I think maybe we start with trying to leverage the standard library as much as possible, and then we kind of pull out like the things that we care about later. Seems reasonable. Seems reasonable. Okay. So I guess let's start out with like the types that make sense for this thing. So we know that we have this thing. The question is, do we think that sub allocator is like a different type than the root allocator? That might be nice in some ways and not nice in other ways. So let's for now assume that we'll create sub allocators that have the same type, right? So we're gonna have like make sub alloc takes in self as a sphalic and returns a sphalic. That seems reasonable to me. And we said before that we are going to track pages. So I guess we're going to have some sort of like page allocator in here. And here he's going to have like allocated pages. I don't know. There's going to be some data type here. We have to think about this a little bit because we don't really know if this guy's kind of like the root allocator, then working in units of like, if we just tried to do like std array list of allocated page here, right? That doesn't really work too good because this array list needs some sort of allocator. And like, I guess we could make this whole thing depend on like yet another general purpose allocator that sits on top. But it would be kind of nicer if this guy like could work without anything but the ability to map pages. So like we could imagine that maybe we have some sort of like paged like page arrays list or something that like kind of like acts on the unit of pages. Maybe we make like a linked list of pages. Yeah, like page linked list, who's gonna have like some sort of like internal data. Okay, let me think for a second. Pages is wrong. We're gonna call these blocks. That's kind of the names that we've been using before. We've kind of been using the name like, okay, so when we ask for pages from the operating system, we can get something that's like 4K, but we can also get something that's like any multiple of 4K, right? So we might get some pages that are like really big. We might get some that are 4K. We might get some that are like really big, right? Like, right? Who knows? Who knows? And so we've been using the term block to refer to this. I'm probably dumb, don't know what you're much about allocators, but I'm imagining you're trying to do is this. I don't know if I want to look. Yeah, I don't know how much I really want to. I want to like come up with what I want and then figure about things later. Why not use a tree? A tree of what? Yeah, no cheating. Yeah. So I'm imagining that this thing has a list of blocks that he's allocated, right? So I guess this thing is literally just going to be a slice. He's going to try to figure out where the pointer starts and where how long the thing we allocated was. And I guess we also have the extra constraint here that we know that this thing is aligned to a page boundary, right? We do know that, which I think we have a type for already. We already have this here, block, right? So let's say that we have some sort of like allocated blocks. And let's say that we have like a page linked list of block here. So we kind of say that like we're trying to store elements of block, but the storage for this thing is going to be backed by a single allocated page. I think that's pretty reasonable. Yeah, you don't ask for pages. You tell the OS to create memory mapping, which just happens to be page aligned, so it can be nicely committed to main memory as it's being touched. Just happens to be seems a little strong to me. I think that like all modern systems require pages, I think, right? Because like my understanding is that the virtual memory mapping in like the memory management unit is on the level of pages, or else it would be too big. Um, and so I believe it's more it's a little stronger than just happens to. I think it's like maybe Linux could do something, or maybe like the POSIX standard could do something different, but I think in practice everybody has to give you pages. Okay, so here's what I'm thinking. If we in our block allocator, if the only unit that we have here is like things of 4096 plus size, I kind of like the idea of having like a list of elements, page linked lists. So I kind of like the idea of having like one page of elements at a time, right? So we're gonna have like a bunch of stuff, and here we're gonna like fill in, you know, all of the things that we want to care about. In this case, it's gonna be however many blocks we can fit in a page. Hello. Seems like everybody's working on an allocator these days. Have you seen the new one STD? I did see that there were a bunch of commits in the Zig. I did see a bunch of Zig commits, but I didn't look at them too closely. I kind of figure I'll look at them when 014 comes out, which should be soon. So I'm imagining you have this stuff, right? And then eventually we'll run out of space in here. If we were to allocate like too many blocks, which you know is possible. It seems unlikely, but it's possible. Then I think that we want to basically just continue the list in another page, right? So I guess in this world, I want some sort of structure. What do I want? I guess we can kind of assume that we'll work in the units of a single page. I think that's fine. We don't have to work in blocks. We don't have to worry about variable size pages or whatever. We'll just say we get one page at a time. One page at a time. And so this guy's going to take in some sort of like element that he's stashing this thing. And hard deadline of February 17th. Hell yeah, dude. Let me think for a second. So this guy, this thing we return needs to be the size of a page, or at the very least very close to the size of the page. So we know that we're gonna have to store like next, which I guess will be like one of these. Yeah. Who's null by default. And then I guess we just want like elements of this thing that fill up the rest, right? So we kind of want like size of t. Like, okay, can we do like next pointer is this? We want like not like capacity to be like the page size minus the size of a next pointer over the size of these. And then we have to be really careful about alignment too. But we also don't really know what order these things are going to be stored in, right? Like if we do like capacity, we have these as well, right? If we do this, then I don't know if we're like guaranteed which one of these comes first. It probably depends on their alignment or whatever. It would be kind of nice if we could like force a certain alignment so that we can guarantee how many elements we can fit. That'd be kind of chill. So is this what we do? I think packed structs might force ordering in some way, although I'd kind of prefer not to. There's also like extern structs, I think, that follow like C ordering rules, which is probably ideal here. I think it's like Zig, C compatible structures. Uh, it's like it's packed and something else. Zig reference extern. Yes. Okay, that feels right. Can we look up extern struct? Here we go. So extern struct has in-memory layout matching the C ABI for the target. If well-defined in-memory layout is not required, struct is a better choice, but we want something well-defined, so we'll use something well-defined. Okay, so let's say that we'll return ret here, but I would love to be able to do some things like make sure that ret that the size of ret is less than or equal to the page size. That's really important here. That's really important here. And then I guess to kind of follow follow conventions, maybe we say that we have some sort of items, right? And this items takes in yeah, const self is equal to this. This returns a slice of t. Okay, that means that here we also need to stash the length of this thing. So that means that we kind of need it would be kind of nice. Maybe it makes sense instead of doing next pointer here, we have like metadata. And we say everything that's not the storage lives in metadata. You know? And so we kind of take this stuff and put it here, which means that this thing doesn't need a name anymore. And so then this is just minus size of metadata. Yeah. That seems reasonable to me. So then we have like self storage from 0 to self metadata len. Chill. That's how we get our items list. Except that we don't know if we want to iterate everything. We don't get like one nice slice like this actually, right? Because you have to traverse the linked list. So it probably makes more sense to have like some sort of iterator type. Who's going to return a t, maybe a pointer to a t. Okay. And I guess he'll probably store like an index as well as which page he's looking at. You know, list segment probably is the name for this. Yeah. This is starting to seem kind of reasonable. So here we say like if our index is equal to this list segment metadata len, we set the list segment is going to be the next one. Yeah. Or else return null, I guess. Yeah. And then we reset index as well. Okay, this feels reasonable. Then it's literally just like self list segment storage at index is the thing we're returning. And we have to increment the index. Yeah. Okay. Uh-huh. Uh-huh. So this is just like return list segment is equal self. Okay. So that's looking pretty good. Um I think that this is actually this I think I want like the root and like individual segments of this thing to be like different types. So kind of this stuff is about like a page elem or like one like list segment, I guess is what we called it. And this is the thing that we want to have like, you know, well defined memory. Which I guess we can't do here. So I guess we'll do ret list segment here instead. There we go. Okay. And so this is this stuff. Cool. It's kind of like all of this goes in the list segment. Okay. Yep. And then our like return structure here is just going to say root is some list segment. There we go. And by this, I probably mean a pointer to the list segment that is going to have to be allocated from the page allocator. Sure. Okay, cool. Um, Page allocator here. Okay. So I think that we can probably get away with using Zig's like the standard library's page allocator here. I haven't really taken a look too closely at it, but I know it exists. So they kind of have like, you know, all of the like, oh, if you're working on, dude, who the fuck is using Plan 9? That's crazy. But you know, they have like, which allocator should we use depending on what operating system you're on? So if we have an operating system and that operating system has a page allocator or a heap, then we might return those things. So do we have those things? No. No. So we're probably in like this case, page allocator. I guess we can check. If we use like std mem page or heap page allocator, this allocator makes a syscall directly for every allocation free, thread safe, and lock free. Okay. So I guess we can probably assume that we're in this guy, the page allocator. And we can assume that we're kind of doing this shit. And it looks like it's literally just like, we're just going to map and unmap. And they align to the page size. Okay, cool. So we probably allocate a list segment here. Yep. Uh-huh. Okay, that seems kind of reasonable. Yeah. Okay, so now we are going to use this structure. I guess this does need a D in it now. And he is going to, you know, what's he gonna do? He's gonna iterate over each list segment and free it because those are individual allocations. So he's gonna go var segment is self root while segment metadata, I guess while true. Uh I guess while segment, I guess. Yeah. Yeah. TIL, there's malloc stats for libc's malloc. Oh, that's kind of hype. I didn't know about that. That's kind of cool. Okay, while segment. Well, maybe we'll call this opt so that we can write segment here. And we want to go by pointer here. Yeah, it's something like this. Okay, so while we have a segment, we free that segment. But before we destroy it, we check, you know, I don't know what happens here if I like reassign before doing this. So I'm just gonna do this. I'm just not 100% sure, so we're gonna do some superstition here. Because like I think that this would do a copy out if I did this, maybe not. But I know I've seen some stuff occasionally where like you think something's gonna be a copy out, but then Zig optimizes it to not be a copy out, and so I'd worry that changing segment op while holding this is like an invalidate segment. I would just worry about that. So this is just an easier way to make sure that doesn't fucking happen. Okay. Yeah, seems reasonable. Seems reasonable. Um, we could also hold like a last in here, but I don't think it matters. I think that the chance of this ever getting like significantly large, like more than a couple pages large, is like pretty unlikely. So I think we can just do it like this for now. Okay. So now I guess we need to implement some sort of push function for this thing. Right, so he's going to take in some sort of val. And he's going to need the page allocator as well, I guess. Like, just in case. He's going to, like, loop over all of these things. So, like, last segment. What do we call this thing? We call it a list segment. So he's going to be like, this is self root, while segment has a next field. Okay. Okay, there we go. Yep. So we we have like the last segment is self last segment. If last segment dot metadata len is equal to list segment capacity. Yep. If that's the case, then we need to append a new segment. We'll just put unreachable for now. Append a segment. We'll come back to this later. I don't really want to do this right now. Uh, then we just set the thing. So this is at last segment storage at last segment metadata len is equal to val and last segment metadata len plus equals 1. Okay. Hell yeah. Fix me extend list. I guess we might as well just do it. It's pretty easy. Yeah. New segment is this. Last segment metadata next is equal to new segment. And last segment is equal to new segment now. Boom. Easy. Easy. Okay. So that's a container. So our block allocator now has a list of allocated blocks. And I think here it's literally just like, if we're going to try to leverage standard library types, then this guy needs to implement the allocator interface. It's the only thing that makes sense. So I guess we take his little vtable and slap him in here. Boom. Allocator vtable is equal to this thing. Okay. And we need to implement these functions. Okay, so these guys go out here. Here we say, we take this thing and we say that he is implemented by block allocator dot the thing, delete to the line, comma, we go again, and then these have to be equal signs actually. And then here we need to do a little macro magic to say that, this is a function of this thing, delete till that, and then go to the end of the line and make some squiggly braces. Okay, cool. And I guess we are, every time we allocate something, we're literally just wrapping the page allocator. Right? So we have like, we're literally just calling this. But before we give it back to whoever called it, we append it to our list of allocated blocks. So that means that we need like, this is a block allocator that comes from a pointer cast, a line cast of context. And then it's literally just like self allocated blocks. Oh, it's append in this language is the typical word here. Uh-huh. Uh-huh. So we append using page allocator and return. I guess we kind of want to know the slice that was returned. So that means like we need to make an assumption about what this will return, or we can call alloc with options here, and then that'll give us the slice back. Maybe. So we're looking for len amount of these things with this alignment. But like, we want this ret adder to stay, I think. I think. I'm not really sure. Maybe this is fine. So here we want to pass in the alignment. Uh, Maybe we just, I'm kind of down to just kind of calculate the size ourselves. I'm kind of down. Um, Align forward log 2. Um, I guess it's literally just length. Yeah, I guess we just assume that the alignment of this is like um less than or equal to the page alignment. Yeah. Like something like this. Yeah. Sure. That way we just know that this thing is going to be a rounded up version of that. So we take like stood uh mem align forward log no. Yes. I think it's like this. Yeah, so we say that the length of this thing that we got is this. Cool. So this is the like full block len, I guess. And so now we can return this from 0 to full block len. Yeah, nice, nice, nice. That feels right. That sounds kind of right. Let's just not do resize for now. We can come back to this, but for now, I don't think we need it. And then for free, I guess we have to find the if the block in our list of allocated blocks and remove it, which means that we need like a swap remove on our thing here. But for now, we'll just write unreachable here because I don't want to think about it, and we can come back to it after. So we're gonna like look at the block list. And we're just gonna fucking rip the list for now. I think. I think that's fine. Because I think that this should be kind of rare. So if this ends up being like a point of like actual slowdown, we'll do something better. But for now, we can just go in here and we'll say, let's just like check every element in the list and see if its start matches up. No. So if this guy is equal to lm pointer, then this is the one. I guess. Kind of weirdly, we could kind of do it here. Yeah, that's kind of weird. So we're kind of assuming that there's no ordering to these things, which I think is fair. I don't think we need it. But surely that invalidates the iterator. Yeah. So I guess if we just break though, if we just break, that means the iterator now has that state. Yeah. That's fucked. But I guess actually kind of works pretty well. So we might just like end up with like blocks with smaller sizes, like, and that's okay. So I think append here. Now I don't like this word. Insert, and we'll just put a note on this. May not insert at end of list smile. And then this swap remove now just has to go. We'll call this. This has to go here. Yeah. And so it's literally just like self storage at index is self storage at metadata len -1. If len is greater than 0, we kind of like move that thing back. And then metadata len -1. And I guess we don't have to check this because nobody should be swap removing something that doesn't fucking exist. Oh no, wait. It's greater than 1 here. That's what it is. There we go. Yeah, it seems kind of fucked, but it works. Okay, that's like a maybe. That's a maybe. So now what? So we have this like theoretical page allocator that tracks with block, or I guess block alloc with block tracking. This thing like theoretically exists. We have no idea if it works correctly, but like we've written some code that we think will do it. Now the next part is to try to make an arena or make a general purpose allocator based off that. Okay. Yeah, so we'll kind of ignore this like allocator tree shit, and we'll just literally just try to make a general purpose allocator that works with that thing. So root block alloc is a block allocator initialized, which doesn't seem to exist. I thought it did. Yeah, I guess we need to make one. Okay. So allocated blocks is page linked lists of block initialized with our page allocator from the system. And presumably this can fail, right? Yeah, it can. Which means that this can fail. Cool. Okay, now can we initialize a general purpose allocator based on this thing? I remember seeing there's something in the config here that lets you override the backing allocator. Right, there's this thing. This isn't even in the config. Okay, so let's say that we use the default config and we initialize this with backing allocator is equal to root block alloc. And then can we use our little test from our previous version of this thing that like kind of just spams allocations? And let's just kind of look at like the state of that thing at the end. Okay. Okay, so first of all, let's just like build this and see where it falls over, because surely it doesn't work. Okay, so extra structs cannot contain fields of this type. So I guess that probably means that just the metadata type also has to be an extra struct for that to work out. Okay, capacity. Extra structs cannot contain fields of this. Ah, gross. Oh, that blows. Okay. I guess we'll just do this and hope that this assertion at the end will tell us if we've done something fucking stupid. Right, so this thing has to be the right type. So root block alloc dot allocator, which means that our block allocator needs a allocator function that takes itself as a block allocator and returns an allocator, which means that we need to do like context equals self, I assume, pointer. And then vtable is equal to allocator vtable, like this. True. That means that like this guy to work does need to be able to track allocated blocks, which means he needs to be variable. That's a really good point, sir. Okay. There we go. Fuck that up. Okay. Log2 int at 773 is pissed off because I probably forgot to type here. Okay, what's next? Align forward at 775. Can I just make here? Okay. Slice of non-array type. Ah. So here we just need to propagate the failure. Expected this, found that. Okay. I'm just gonna catch unreachable here because this should never fail. But if it does, we're like our tracking is just totally fucked. We could put a fix me on here and say drop ret, like free ret now on failure and return null. But this will like never happen, so who gives a fuck? No field name swap remove here. Oh, this should be a list segment. Yeah. Okay, that all makes sense. That compiled, which is kind of nice. But we definitely are not working. So it's here. When we try to inspect the metadata segment next, he's like, yo, bitch, doesn't exist. Which kind of makes sense. We weren't really expecting a perfect first run. Could you use stood meta has unique representation to check there is no padding in that struct? That's interesting. Has unique representation. Has a unique bit pattern representing. In other words, T has no unused bit and no padding. But I think that I'm okay with padding. Maybe I'm not. Yeah, maybe I'm not. Yeah, that's not a bad idea. Not a bad idea, but let's start with where we're at now. Okay. I guess we probably just never initialized our root segment. That seems quite likely based off what I'm seeing here. Right, so this guy has to be initialized with list segment, I guess. Okay, and then that means that probably the next guy that we make also. well, not when we didn't. Sorry, when we allocate the next one, new segment is equal to a default initialized thing. Okay. So that's good. This guy like didn't crash at the very least. And now we can kind of inspect how many blocks have been allocated right now. So can we look at this? I don't know. Let's just pick a block and see what it says. Okay. We don't need you to be here. Okay, so it looks like we have a bunch of blocks in here, which is interesting. And it looks like they are all... Can we maybe write block? And we just write like block linear. Let's see how many blocks we've allocated and what size they're. So we have like blocks of varying size in here. Cool. And if we run dinit on our general purpose allocator, we should hope that all of the blocks disappear, which they don't, which means that like there's something really wrong here, right? I would think, unless GPA dinit doesn't free all the memory. Oh, wait, we have to free the memory ourselves. I'm a dumbass. I'm a dumbass. We have to free our memory. Not just dinit the GPA. That's the whole point of this. Okay, so now there's one block left at the end of all this. What if we dinit the general purpose allocator as well? So there's a little bit, I have a little bit of concern there. I feel like there's something has gone wrong here. I feel like we should have no blocks left if we dinit everything. But at the very least, it's like close. It could be something about this. Yeah, I think that's greater than 0 here. There we go. Okay, so if we free everything that we allocate in our entire application, then we have no blocks left in the block list, which is like a really good sign for us, right? Really good sign. It would be nice to have some sort of check on this thing that like if we free this block allocator, that it really does like free all system memory. But I guess I just won't think about that too hard right now. Sure. Also, so if I do GPA dinit here, oh, he does complain about all my misallocations. Cool. Okay, cool. Cool. So my other question is does GPA dinit, do I need to worry about anything? It looks hand wavy, like he's not gonna like pull any memory for himself. There's like retained metadata. This thing, but this retained metadata is off by default. So it seems unlikely that the GPA itself allocates anything. So I think it's okay. And even if it did, it would allocate it from the page allocator. So it doesn't matter. If we just like nuke the page allocator, everything should go away. I think we're fine. Okay, cool. So now we have this like block allocator and we can start building our like tree of shit on top of it. So how do we want this to work? How? I don't know yet. So we are saying that at every level of this thing, every level of this like tree of allocators that we're making, someone might use a general allocator right? Or it might use an arena, right? In fact, we're going to try to trend towards using arena allocators, but like, you know, we're going to use the general one in some cases when we have to. Now, what kind of sucks here is that there's going to be self-reference between these guys, right? If we want to like create a tree of these things, and these guys are pointing to this, it kind of means that like at every level other than the root level, even at the root probably, I think we kind of want everything to be a pointer here, just because it like simplifies things. And I guess the pointer to this thing can come out of its own arena? Am I stupid? What happens if we do this? So we like, create our block allocator. I guess. Hold on. We can get there. So we have some block allocator, and we should call this block alloc. Okay. So arena is like arena allocator initialized with the block allocator. Okay. Then is this stupid? So far we haven't done anything wrong. So far we haven't done anything wrong. Okay. What is phallic? It's supposed to be this like allocator tree, I guess. We kind of talked about this at the beginning of the stream. But the idea here is we want to have like sections of our application that can be deinted at in a batch that can do either scattered allocations through some sort of like general purpose allocator or arena allocations through an arena allocator. And so phallic is going to be like our attempt to model that thing, right? So the idea here is like an example usage of this thing, right? So we're going to like create like something that lives for the lifetime of the application. Maybe there's going to be some component of the application where we're going to split off a subtree. So when we call full app deinit, it should deinit the whole subtree as well, but we should also be able to like reset the subtree as an individual component. That's kind of like the idea here. Okay, so I guess we have like arena is the arena, but we need to swap out the backing allocator for this guy. I guess like I think I saw in the arena allocator they have this state struct that doesn't hold allocator here, which is kind of hype. So we might be able to get away with holding arena allocator state here. Okay. Which makes all of this kind of just work okay. And now all you have to figure out is how the fuck do we make this general purpose allocator? Does the general purpose allocator have the same thing? No. So I think that the I think if we do this, it'll work, however fucking stupid it is. General purpose allocator backing allocator is equal to now ret lock allocator. I think that kind of does the right thing. So we'll just say here, general purpose allocator holds a reference to the backing allocator, which needs a stable memory location. Yes. Block, we want to back with the block allocator, and which means that we need to put the block allocator where it belongs before pulling out the runtime allocator interface. Okay, that seems kind of reasonable. That seems like, somewhat reasonable. I mean, that's not crazy. That's not crazy. Okay, so then, like, to make a sub allocator, we'll figure that out later. We'll figure that out later. So let's now start with trying to create one of these sphalics. And then we don't create this GPA. We use sphalic general here, allocator. And then here we don't create this blue block allocator anymore. He's owned within sphalic as well. Okay. We do need to return the return if you think about it. Arc beat you on the new alloc race. Sorry, that means you have to give up now. Best delete the whole repo too. Yeah, well, it is what it is. I don't really care at all, to be honest. Did I just write ret semicolon? Dumbass. Return ret. All right. Okay, so this guy does have 2 blocks remaining. And I guess that's because we need a DINIT on this guy. Oh, yeah, I guess that kind of makes sense. So the 2 blocks remaining. I'm actually not sure. I'm actually not 100% sure. I think that this guy, he definitely allocated a block in the arena. And maybe he allocated one in the general purpose as well. I'd be curious to see if we did like general DINIT here. If we lose one of the 2 remaining blocks, we do. Okay, so the general purpose allocator has a block inside that he's allocated, and then the arena does. So every single one of these guys has an overhead of 8K, which is maybe too much. Maybe too much. It might be nice if like these guys are lazy, but I think that we should like reserve the like space optimization here until we see how many of these things we're naturally creating, right? If we're creating like 4 in our whole app lifetime, who gives a fuck, right? If we're creating like 100, then it's a problem, right? So we're gonna say like note, currently each sphalic has 8K of overhead, because each of the child allocators pull in a page. Don't make these willy-nilly, but really who cares? But for now, but also don't make these willy-nilly, I guess is what we'll say for now. And like, can we reduce overhead, question mark? Okay. So the other thing that we could try, I guess. Okay, first of all, let's make a checkpoint. We've done a lot of stuff. I guess, oopsies, main.zig. The other option here is we could make like a root item that is separate from the rest. I guess let's like think about how we want like the children to be tracked. I kind of expect that children will just be like a linked list of Sphalic. This is kind of like the dumb initial solution, right? And then every time we like make a new child, we literally just use our own internal arena and make a child out of that thing. Because this arena, these things should never be reset without resetting the whole page allocator, is kind of what I'm thinking, right? So I think it's like totally fair to say that like our children are just going to come out of this arena, owned by our own arena. Yeah, that seems kind of reasonable. Seems kind of reasonable. Okay, so that means that it should be pretty easy. To split off a new one. It should be pretty easy. So we call it make sub alloc. And I guess this will do the same. Yeah. Can I inject observation? Sure. We'll see your observation. You might tell us that we're doing something fucking stupid, but that's okay. That's kind of the we're exploring. So I think that here we want to return an allocator, I think. I kind of feel like this stuff, I don't want people accessing them directly. So I kind of want to do kind of like, say we have some storage here. Just kind of to discourage, to discourage that. Reusable allocators use B trees or red black trees, or null and craving allocators use linked list. Yeah, I mean, I think that's what I'm doing. This, I'm expecting to reset by just walking the linked list and deleting everything. And then the general allocator comes out of, like, yeah, I think that, like, so everything here is, like, backed by block alloc, right? Everything in here is backed by this. So when we reset each chunk of our thing, we're going to walk our children, reset each of them, who will each have their own page allocators, I think, and then reset ourselves. And so I think that's fine. I think it's fine. Right, so you're not even going to reissue memory blocks. You're going to hold after free until someone ends. I think that I'm not going to support free at this level. I think the general purpose allocator that uses this guy will be able to free segments from him. But I don't think I'm going to be able to, I'm not going to say that you should be able to free anything from the like child arena or from the block allocator. Those are just like, you just wipe the whole thing. That's what I'm thinking for now. We'll see if that comes back to bite us. But that's how I'm feeling. Okay, so this is backed by the block allocator. Got it. Then I'm caught up, and a linked list makes more sense here. Yeah, that's kind of what I'm thinking. Thanks for the input, though. So, let's do this. All right. So now when we make a sub allocator, we have to create a new one of these things. And I guess he literally just makes his own page allocator. We're kind of like, it might be nice to have like all pages attributed back, but I guess like that doesn't really work really well, right? In the world where we have like root and then like sub, right? If these guys all kind of worked with one page alloc, right? Alloc. And I want to reset this guy, then that means in the root we have to write down all of the pages associated with this sub guy and reset them. So instead, what we'll do is we'll just make each one of these guys get their own page allocator, and they'll unmap themselves as they need. I think that's reasonable enough. Reasonable enough. If it were me, I would just call mmap here. Yeah, I mean, I think that like that's we've got like a thin wrapper around mmap that just writes down also which blocks he's allocated so that he can free them automatically, right? Because when you mmap, you need to write down the other side. I guess we could do the trick where you like mmap just like a mega big range, but then like as we split up off sub allocators, this is a reverse arena. I don't know I don't know if that's like a word that exists, but maybe. It's not. I mean, it does kind of feel like there's some sort of backwards shit going on here, right? Like we're writing down the pages and freeing the pages, which is different than like the arena usually would. There's something like that's not normal here, but it feels like the reasonable way to make what I want. You want sub allocators that can reclaim, but a global that tracks the children. Yes, exactly. I want the ability to reset this guy without resetting this guy, and I also want that when I reset this guy also goes away. Right? Because then the for the vast majority of cases, I don't ever have to like deinitialize this sub guy. The only time that I would ever deinitialize him is if I am resetting intentionally for some like some like in some event loop, right? We it's like, oh, time to regenerate the sidebar, we'll reset the sidebar allocator. But for the vast majority, everything should be handled by the root. That's kind of what I'm imagining. Okay, so I guess it's literally just like we try to make a new one, and I guess we do technically still need to error defer here, even though this is like kind of like the thing we're trying to solve all around. I guess using this type of shit here is fine. Yeah, you call that a reverse arena because the child can free but the parent can't, which is the inverse of an arena where the child can never free but the parent can't. Oh yeah, that sounds right. Hocus pocus with the bang CPU arch again. One day we'll do it, but for now, you have to guess. And then I guess we just try like children. I guess there's no error for here. It's just there's only prepend here, I guess, which is fine. Oh, that's kind of nice. This isn't even try, I bet. This has got to just be free. Yeah. That's kind of neat. Eggs 8664. Saying eggs instead of X is very funny. I've never really thought about that one, but that's definitely one that I'm going to start using. It's really fucking stupid. Okay. So then I guess we also have like a reset here. And he's going to okay, so this is a little fucked, huh? So this trick at the beginning where I said where we can allocate ourselves from the arena allocator that we just made is not true. Because we would love to keep ourselves alive. We would here the whole point of this was it would go like block alloc dinit and then self arena, like we want to like reinitialize this thing essentially. It's almost like we want to go like self block alloc dinit and then like self is equal to something like this, right? So that means that we have to solve like the self reference problem a different way. I mean, a lot of this gets solved if we replace the general purpose allocator with something else. Let me think. So general purpose allocator, the only reason that we have self-reference is because of this guy, this backing allocator thing. And so I guess we can kind of solve that by here saying like if we do this where when we retrieve it, we quickly swap out the backing allocator for the actual backing allocator, right? Because then we kind of say, while you're using this guy, Sphalic needs to have a stable memory address, but like otherwise go wild. Yeah, and here we'll just note, like Sphalic structure may be copied and moved around during initialization. Ensure that the self-referencing GPA is pointing to the right spot. And we'll write hack here because I'm not really convinced. I don't really like this solution, but it should do what I want. Should. And that means here, now we don't have to do this like bullshit. So first of all, is arena state, can I default initialize this guy? I can. So it's almost like both of these guys, I'm like totally fine to default initialize now. I think that feels okay. It feels like we can do this. And now the only trick is that when we make a child allocator, we should create his storage from our arena. I think. Yeah. And then yeah. That feels maybe okay. That seems maybe okay. Maybe this guy, this does need to return a pointer because we do want to make sure. I guess he could just live here. Because, well, the singly linked list, I actually don't understand. Oh, it's singly linked list of Sphalics. Use pointers to Sphalics, I guess is probably how this is supposed to work. Hello, just spawned here. What is he doing? Yeah, we're, the backstory is that we're trying to remove these unrun error differs from our program by basically trying to make sure that we can batch allocations. This would normally be done by normal people with like arena allocators. But arena allocators, I don't think retrofit into my current application very well because there's a lot of components of my application that expect to be able to like free memory, like individually, free individual pieces of memory, which arenas aren't really built well for. And so I'm trying to take the idea of the arena that says we have a pool of memory and we can free that whole pool at once, but also allow like scattered allocations throughout sections of the pool. And then I also want like a pool tree, right? So like we have like, you know, a root element and some of these like subsections of this guy could be like reset individually. but are also kind of controlled by this root part of the tree as well. Because there's like components of the application that like I kind of want to like say this thing has like 100 allocations coming from it, and I just want to like kill them all. I don't give a shit about any of those anymore. Let's reset this whole section. There are like reasons, like the sidebar part of our GUI is something that does that. And yes, that's what we're trying to make. Some sort of like allocator tree. Can those frees be noops if it's an arena? Well, that's the problem though, is that there are parts of my application where if I just used arenas as it's written today, we would get like memory explosion. Like I saw parts where like something that should not be taking very much memory at all was taking like 20 megabytes because of like just the way that like the memory patterns of certain areas of the app. And it's like we could fix all of those, right? There's no reason that we couldn't use an arena everywhere, other than because we're not starting from scratch. We have an existing code base that's like using array lists as ways to generate stuff, right? And it's just like if you like slowly build up an array list, it's going to waste a lot of memory. You're going to basically use like 2x the memory that you're supposed to use. And like, or we're like holding stuff and later we're like, oh, so we want to like write down this text. Somebody called like in our GUI framework, as an example. We have like, you know, a label, right? And this label has text in it that it like says every frame, like get latest, right? And so then like our application is going to have like some text in here somewhere, right? And the GUI framework as like it's both reallocating continuously and rarely freeing it all at once. Yes, something like that. Yes. So like our GUI framework, this like label widget, this widget is going to live for the lifetime of the application, right? But if it wants to regenerate all of these like GPU buffers that like actually like lay out the text, right? We only want to do that when the text changes because like generating this GPU buffer is like relatively expensive, right? We have to like do text layout, we have to like render the characters into like the atlas if they're not there, then we have to like create a GPU buffer that tells us where to place all those letters and where to sample them from the atlas, right? So what we do is we say is this text like we'll have like last text here, right? And so like when what we do is we like check this text that we get from the app and we say, is it different than the last text? If so, regenerate, right? Which means that we have to store this last text. And we don't have the guarantee in the GUI framework side of things that like the thing that the app text returns is gonna like live forever. In fact, we know for sure that in the future this thing's gonna change. And when it changes, we have to notice. So we have to copy. So this has to be an alloced thing because we have to duplicate it and we have to store it for some unknown period of time. Right? I guess we could store like a buffer in line. We could say like we have 4096, and if your text is less than 4096, we're good. If it's bigger than 4096, get fucked, right? We could do that. But instead I went this way, right? And so that means that this like long living widget is going to free memory a lot of times. Because also, the other time it does some of these reallocations, I mean, there's like other reallocations that happen here, but it also reallocates if like the window size changes, right? And so like the ability to have a pool of memory that we can also have frees in that don't waste memory like forever and ever and ever is like really important for us in order to retrofit nicely, right? So that's why we're doing it this way, where we're generating like our own special tree of allocators. And I haven't really seen people talk about doing things this way, but I also didn't look very hard. I'm not much of a no cheating, as we say around here. Okay. Okay, so now the question is does this allocation scheme work? Ualloc doesn't realloc on resize? Oh, you talk. Oh yeah. Okay, so how do you like? You just like append things to the list, right? Stop making so much progress. I haven't caught up with the YouTube pods yet. Sorry. I mean, the good thing is they'll live there forever, so you can always just slowly keep you can always catch up. Well, you can always get closer. Well, you can always advance. Okay, let's just try to build. So our singly linked list, can he just be default initialized? I haven't really worked with this thing before, so I don't really know what it's like. So this now is general, like this. And he needs a variable sphalic now. And then what's he pissed about? No field named allocator in general purpose allocator. Oh, it's backing allocator. Okay. So does that like run? It does. That's kind of hype. And then if we don't do our dinits here, we have like a bunch of allocated blocks. Feels kind of work. Feels like it's kind of working. Feels like it's kind of working. Okay. So, oh, we have to be careful here though. This allocated blocks list now, if we want to like dump the entire state of like our whole tree of memory, I guess we have to look at like our allocated blocks plus the block sizes of all of our children. Yeah. So let's add that as like a feature because for sure, as like our as part of our like actual application, we're going to want to monitor the total memory usage of like certain segments of the application to make sure that we're not going like out of bounds or anything. Like to make sure that like our memory usage is useful and help us like track down if there's like memory leaks and stuff, which there shouldn't be with this game, but if there were, you know, we should probably be able to take a look. So I like the idea of having something that's like total memory allocated. Okay. And so he's going to look at all of his children. Does this like singly linked list thing in Zig, like what does it give us? Not a lot. So I guess we just look at like we probably just have to inspect the insides of this thing by our hand. So we probably look at first, which means we have to know what a node is. Okay, sure. Sure. While IT. So there's gonna be a. Is it like. I guess here. We make a type for this thing so that we can kind of poke it by name. Uh-huh. And where were we here? So this is going to be a children. I'm hoping node is public. Yes, it is. Hell yeah. So while it val, uh, we say total memory used is a usize here. We increase this with val dot data dot total memory allocated. Allocated. Okay, and then that means that here we go, it is equal to val next, like this, which I'm hoping will work okay. And then we should be able to do something. I guess we also have to like use our list as well. So can our block allocator for now also say like total memory like allocated? Okay. And it's gonna go for, we have some iterator given our allocated blocks iter. Yep. This gives us a block. Okay. And then we say var ret is equal to 0 is a usize, and we return ret down here. And for each block, we plus equals the block len. Hell yeah. Okay. So then in our this guy, this just starts with self block allocated. Then we add in all the memory from our children, we return total memory allocated. Hell yeah. So now we can just print like root allocator is using svalloc total memory allocated. 859 is, oh, pointer. Pointer. Okay, fine. Fine. Okay, so we're using 405 kilobytes here. Now, it would be kind of fun now to split off two children from this guy. So we're going to say, like, child 1 is cephalic make sub allocator. And child 2 is a different allocator, right? So this guy has two children now. And I guess what we're going to do is we're going to go for each of these children. Let's use a general allocator for now. For each of these guys, let's run this like loop of kind of filling up this list of allocations. So yeah, we'll start here. We create a random number generator. This guy is going to use maybe the root allocator at first. Yeah, we're going to use the root allocator to make this buffer. Sure. And I guess we can use kind of like the arena here. Oh yeah, this is starting to feel kind of nice. This is starting to feel kind of nice. Then we're going to maybe use child 1, maybe child 2. General allocator off rip here. Okay, so we have like a bunch of random allocations that are backed by child 2. Then we go through this, and I guess we have to de-init this thing with the correct allocator, which is a little bit of a problem. So instead of trying to mix the allocators, let's actually just make, I think we'll just do this for both children. So let's do like make rand allocations, or like cycle rand allocations. I like that. So this is like, yo, this list of allocations is backed by this allocator, and here is your buffer. Yeah. So then we create one of these guys with like child 1, and we'll call this like child 1 allocations. This is with rand alloc child 1 allocator general. Yeah. And then we'll do child 2 as well. Okay. Then all of this stuff comes from this. And we need our random in here as well. Okay, cool. So now we should be able to be like, cycle random allocations given child 1 general allocator and child 1 allocations and rand. And we do this with child 2 as well. Allocations, actually, because I spelled it wrong. And so now I would love to see, you know, the usage of each of these. So what we're hoping to see is that like the root has some amount. He's actually pissed off for some reason. Oh, because make sub alloc doesn't compile anymore. Okay, why not? Hello? Oh, it's the promote on the allocator? It's in here. All right, so that fixed some of it. Expected a node. Found main alloc. Oh, really? They're really not holding my hand here, huh? Um, I guess it's like this. Um, I guess this is what they want. Oh, I'm supposed to be allocating a node. Oh, that's interesting. Ah, okay, that makes sense. I see, I see, I see. So here we have to like try one of these, I guess. There. Okay, I think that makes more sense. Okay, I think this is what they want. So we allocate a node, the node has a next pointer, we append that, and then we do this. And then like fix me what if sphalic init fails. I guess that's, we don't have to think about that. Child alloc is we tried this off rip. And then if that thing fails, we just fully get rid of this guy, which actually doesn't exist right now. I guess reset is good here. Then we insert this into this thing. We're chilling. Sure. Reset is mad because, this has to be variable for that to work. And node data here is pissed off because, like, I actually don't know what he's pissed about. Expected this thing, found this thing. Oh. Ampersand. Okay. Now, expected type this, found that. Oh, fuck me. So this doesn't work. This doesn't work. Because okay, so there's like allocator state, right? And allocator state, arena state, we should call this. There's arena state. Arena state has like promote, which returns an arena. Then arena allocator returns something that like references the arena, right? Something that refs arena. So we actually have to do the same trick here where like the arena has to outlive this function call, which means that this guy has to be this. And we just have to do the same fucking trick here. We do the same trick here where the arena child allocator is like this. All right. Okay. Which means that this guy needs to hold an arena here. And this guy can't be default initialized anymore. But we can say that arena is state is default initialized, and the backing allocator, child allocator, is undefined. And we'll just put a note here and say that will be injected in arena function call. Valigo, hello, hello. Thanks for the raid. What's up, everybody? What's up, what's up, what's up? Welcome, welcome. I hope you had a good time over there. we are working on trying to solve. Hold on, one sec. Okay, yeah. We're working on trying to solve this problem I have. This problem is that I have a million unrun error defers in my image editor. Gross. Ew. Committing unchecked code? Ugh. You gotta run the code before you commit it, or else, like, what the fuck are we doing, right? The problem here is that, like, the vast majority of time, allocations don't fail. Very occasionally they might, and we, like, try to do our best to do the right thing here, but the chances of us, like, doing something fucking stupid and crashing the program because we typoed is, like, pretty high, right? So we're looking at, like, arena allocate, something that's, like, analogous to an arena allocator. People solve this problem with arenas all the time, right? They say, given, like, a bunch of stuff that you're going to do, let's allocate everything in this pool. And then later we just nuke the pool. And, like, now each individual allocation doesn't have to carry about freeing his memory. Bing, bang, boom, everyone's happy. But we have, like, an extra constraint where arenas, they only allocate by moving a cursor forward. Arenas, like, typically don't support, like, freeze. Maybe they can free the last element by removing the cursor backwards, but, like, every allocation comes from, like, wherever the cursor was at that time. This doesn't work for us because, like, there's reasons. I'm not going to get into them again because I just explained it to the other guys. But, like, there are reasons why parts of our application expect to be able to free memory over a long period of time, right? We kind of have this, like, we want to use our arenas, for lack of a better word, to manage, like, long-term lifetimes, but not, like, short-term lifetimes. So if somebody says, like, I'm going to cache this thing and I'll delete it later when I get, like, a new version of the thing, like, I'm going to update my cache, I'll delete what was in there before. Like, we want that to, like, actually free memory. And so we're working on building, like, an allocator tree where, like, each section of the allocator, you can, like, kind of, like, delete this, which will delete all allocations in this section of the tree. But each node in the tree can do, like, short-term, like, medium-term allocations if they want to. That's kind of what we're making. Right, so we have this, like, sphalic type who has children nodes that are just like himself. And then in here, he has, like, a general purpose allocator and an arena allocator that are backed by, like, his own individual page allocator. And we'll figure out where that's going. Anyways, thanks again for the raid for Lego. Hope you guys, like, enjoyed. Hope you guys enjoy this. But no harm, no foul if you've got to peace out. Okay. This guy does need a D in it. He does not currently have a D in it. But this should be pretty easy. So this guy is a list of all of the blocks, all of the, like, pages of memory that we've asked the system for. We're kind of, like, tracking those as we allocate. We go, oh, quick, write down this page so we can free it later. And all we have to do is, like, actually do that. So we should be able to be like, let's just go over all of our allocated blocks. And for each block, we literally just go, like, page allocator, just, like, free that block. Hell yeah. So that's simple. That solves one compiler error. Expected type this found some shit show at 850. So this guy has to be able to fail, I guess. Which is kind of weird. But I guess when we initialize each of these, like, allocator trees, we do allocate one page of memory. So I guess it's kind of reasonable that that's part of it. Which means that I guess D in it kind of seems like a reasonable thing to split out here. Because we would love to not have to do this tried thing, right? This guy can call dinit here instead of reset, and everyone was happy. Okay. Expected void found some shit show at 899. So that's probably in this guy. We just forgot to write a little exclamation point here. And then error union is ignored at 936 because, again, we have to write tries now. Okay, expected pointer somewhere at free dinit says 765. What is my block in here? Is my block not a pointer? It is. What's the problem? Found. Expected pointer. Found. Oh, double pointer. I see. Okay. So here we go. This is a good sign. Let's see. First of all, we have to find out if these numbers add up. But it seems like the root allocator is using this much memory. Child 1 and child 2 are using these. And it seems like those add up. They might be like maybe 1 or 2 pages off because the root might have some tracking data on his own. Yeah, so there's actually like a significant amount missing here. What is that, 8K? Interesting. Interesting. Where's that 8K coming from? Oh, could be from here when we split off our children. It's kind of surprising to me, but I guess the we probably have one block for something. We have one block allocated for the page linked lists. I guess this guy needs a DNet too, huh? That's probably the problem. Oh, I guess that doesn't really tell us anything. Sure, but so we have one page allocated for the storage of blocks, and then another page allocated for our arena. Which I guess makes sense. That makes sense. So an extra 8K on the root is reasonable. And then if we were to like de-init a child here, the child, if we were to do like here, we go child to de-init, right? We should see. Oh, I guess he tries to access him. Right. So the problem here is that child 2 is still like part of the root, which is kind of odd here. So he needs to like unregister himself as a child from the root if we deinitialize him. Or a child of his parent, I guess. So I guess it's like this. And then on deinit we say if we have a parent, we like look through the like children of this guy. Right. We go like it node next. And then we say like if node is equal to node data, if this guy is our self, then we have to remove it. Is there like a remove function? Remove a node from the list. It is. Okay. Okay, sure. I'm not really 100% sure. Like, this must walk the list again. So this is like, you know, maybe like walking list an extra time. But like, fuck it for now. I don't really care. Okay, there's still some seg faulting happening here. Which means that this must not be working. Removing node from parent. Yeah, so can we say like, oh, because we didn't actually set the parent anywhere. Oops, it's okay, so this worked, removing node from parent. That seemed to have done something. The root allocator now is in fact um, claiming that he's lost all of the allocations that came from child 2. However, oh, I mean, this is just an expected failure because child 2 is dead now, so we can't really check the memory allocated. Okay, that's cool. That's pretty cool. That's pretty cool. What would kind of be nice, I guess, is to like automatically print the tree, but I mean, this is fine for now. That's fine for now. Okay. So now I guess what we want to do is we want to like pause the application here and just take a little peek to see um like what the virtual memory mappings are here. Um yeah, I kind of want to pause and like peek. So there's like a like zig wait for a standard in. I've actually never done this. It must be like stood IO stood in. Read all into, you know, some buff. It must be something like this, right? Like this. There we go. Okay, cool. So now we should be able to say like, yo, at the end of your life, can we like D in it here, I guess? And then wait again. Right, kind of like something like this. Okay, cool. So now the question becomes, let's look at pgrep sphallic cat maps. Okay. So there aren't that many mappings, interestingly. But it would be interesting to see if I hit this. They're kind of the same. So that's a little concerning. Yeah, that doesn't look great. But maybe we need to look a little bit more carefully. Let's just like... okay, what do I want to do? I want to maybe diff them. That's kind of the play, huh? Okay, so A text, B text. And can we diff A text and B text? Okay. So it looks like this went from 138 to 19F to 139 to 19F. It doesn't really feel like we freed that many pages. Right? It doesn't really feel that way. Which makes me really suspect of this. Because we should have freed around like 10 pages here. And it looks like I'm seeing like one here, one here, one here, and 0 here. These are the same number. So I'm a little concerned about like how many pages we're freeing. Can we maybe take a look And in our deinit here, freeing block of len this. We do have to write down the length of the thing we're trying to free. Okay. So that's interesting. Oh. It's because we're not freeing our children. We're looking at our parent, but we also need to look at our children. Yeah. Oh, no, wait. If self-parent, we look for ourselves and remove it. And we also have to go for self-children. Okay. We need to do node data unit. Okay, so now he's mad for some fucking reason. Because this is happening after... Yeah, I'm a little confused here. Std debug print freeing child. So I suspect that we're trying to free child 2, which was already deinited. I suspect. I would like to see confirm that here. No, that's also bugged. So even if we don't deinit anything up front, we're still in trouble. So what is happening here? List segment is self root. Oh, because our children are allocated out of our block allocator. There we go. That's much better. That's a large list of stuff to free. Okay, so can we do the same test now where we run this guy, we cat this thing into A, we deinit anything, and then go into B now, and then diff A, B? Hard to say what I'm looking at. Hard to say what I'm looking at here. I don't even really understand, like... I don't even really understand what this is when I look at this diff. Can we look at, like, diff dash u here? Is it dash lowercase u? Here we go. Okay, so we deleted these 2 lines and replaced them with these 2. So we have 1 page left out of this chunk. Still many pages left out of this chunk. In fact, this chunk isn't even really... I guess we freed, like, from 1 to F here, and went down from B8 to 6.3 here, which is a significant amount, but it's not, like, fully gone. It's not fully gone, which makes me worried that I've forgotten something. Page linked lists. He destroys each page segment out of this thing. Okay. Which kind of makes me think that, like, we're double deinting stuff here. No, because the blocks themselves also have to be deinted. So this is the tracking of the blocks. This is the blocks themselves. Feels kind of right. Feels kind of right. Hmm. Maybe we checkpoint at the start too. So now we can, you know, take the current state and drop to A. Now drop it to B. And then drop to C. And then can we diff A and C? Okay, so we have definitely increased mapped pages here, which makes me think that we're not freeing everything. It has to be. We have to be. Now, I'm curious a little bit if, like, where the bug would be. It's like, it could be that the page allocator here, like, doesn't free in the same way I expect it to. That seems quite possible. It could also be that we're not tracking the blocks that we've allocated correctly. Both are very real and possible. So can we let's like get rid of this child game for a second and use this guy everywhere. Let's see if this is at the very least doing something reasonable. So it was a text here, B text here, C text here. Okay. Yeah, so even just the root allocator here has a bunch of stuff that's like unaccounted for, which feels scary. Okay, what if we take... Can we like encode this? Can we just like put this in the app? Like, is there something in like the standard library that will read our own mappings? That doesn't matter. We can just open proc self maps, right? Dump maps into some name. Okay, so we're gonna take like open file absolute name. And no, this is current working directory create file. Yes. Then we put the stuff in the file. So we content is there like read? There's some sort of like, I thought there might be some sort of way to like just directly read stuff into a buffer, but maybe not. So we'll say proc maps file. Open dir open file. Yep. And we're looking at proc self maps here. Okay. I think this should be const actually on both of these. Then you're supposed to do one of these, I think. Make a little FIFO so that you can do FIFO pump from the like F reader into the writer. Something like this. Hello, what progress did you make until now? We have something that we think is some sort of reasonable tree of allocators backed by like the arena allocator in the standard library and the general purpose allocator in the standard library. Both of those backed with like some sort of page allocator that we wrote that is supposed to like track what pages are allocated. And he's not quite behaving the way I want him to, so we're just trying to figure that out. So here we dump A, we dump B, and we dump C. All right. So you ditch your bump and normal allocator. They're still like in the code because I think there's a chance that we'll want to use them. But I think that it makes sense to start with the standard library ones if we can. And kind of pull in the other stuff as we need. Those are kind of more of like an exploratory thing. Right, so... yeah. That's the idea. They were kind of exploratory, and now that we've explored, we can make better decisions. And yeah, we'll figure it out from there. Maybe we'll find that we need features that we don't have. But for now, let's just kind of start here. Okay, so if we don't allocate anything here, we're chilling. So it's as soon as we like try to allocate anything, I assume that now, even then, interesting. So this is fine too. Allocating 100 allocations off rip, no big deal. That's surprising to me. But now that we've actually put some stuff in those we've allocated some more stuff, it must be something along the lines of like some blocks aren't being deannotated correctly. It has to be. Or we're like not tracking them correctly. Block alloc.allocator. Uh-huh. Is it possible that this guy... No, this guy should never have allocated anything until... The allocators literally had no... The arenas had no functions run on him up until this point. So there should be no reason... Oh, I guess it's here, general. That's interesting. So our general purpose allocator is maybe doing something fucking stupid. But again, like, he can't have done anything until we've run this. I guess it could be that we're adjusting the ranges, like the size of the page he requested. I wonder what happens if we just return, like, do 0 to len here. Instead of trying to, like, adjust the block size to be what we think it should be, I wonder if that's kind of, like, fucking shit up. No. Okay, so there's something here about when we use our general purpose allocator. Is it possible that the general purpose allocator is like doing some allocations that we're not expecting. Yeah. Fuck. Okay. So he's using the page allocator more than once directly in here. So here we're supposed to do. Oh, that's fucking annoying. That's so annoying. Can we turn that shit off? No. Uh. Okay, but surely this memory pool stashes the allocator. Okay, so memory pool returns a memory pool aligned, returns a memory pool extra who calls init, who stashes an arena with this thing, right? So, oh, it's annoying. I mean, that's kind of making me feel like we should use our allocator. I'd be curious to know. I mean, we could probably hack this, but I'd be curious to know if instead of using this, we used our buddy allocator here. We'd have like a better feel. Yeah, we'd have like a better feel at least for what it uses, but I don't really want to do that right now. So I'm gonna hack it for a second. I'm gonna hack it for a second and see if that fixes it. So it's that every time we use the general purpose allocator, we need to go in here and hack the bucket node pool. Was it? It was bucket node pool, right? Was it? Yeah. We need to just fucking hack this shit. So it's like arena child allocator is self block allocator, and let's just put like a mega fix me. This is too far. This is too far. Maybe we ditch GPA. Okay. So that's closer. It looks like probably there's more. Only a test. It depends on what this init does, I guess. It literally just makes an allocator. Yeah, so it should be fine. Should be. But I mean, pretty clearly, if we use arena here, that doesn't happen. If we use general here, there's definitely something still fishy going on. We still have like 4 pages. Oh, that's so annoying, man. I mean, it's got to just be that like someone in here is like, did I miss large allocations, inserts with the backing allocator? So that should be fine. Yeah, I don't really understand how. I don't understand how if the only places where page allocator is used here is here and here, if we swap them out, why it's still a problem. Yeah. I don't understand, but I mean, it's pretty clear that it's not working the way I expect. So I guess we'll just put like, we should like write a test for this, I guess, at the very least, and like figure out the problem. Okay, we're gonna checkpoint, and we're just gonna fucking try to rip it with our own allocator. Or I guess we can just dean at the GPA. That's also just a very real thing that we could do here. I guess that is the fix. Um, force updates. Let's see if that changes anything. Okay. Really? Really? Am I missing something? I mean, we were pretty confident here that the arena allocator wasn't causing any of these problems. It's only when we start initializing stuff with the general purpose one. I guess we might also be like double unmapping if we try to do this, which is a fucking problem. No, because the block allocator should handle that. I guess there could be some resizing trying to be happening here, but then like we'd say resize is not supported, so I don't really see why that'd be the problem. Okay. It feels close. But I also feel like my head hurts. I'm definitely feeling like I'm losing steam, so I want to kind of just like mull this over and kind of call it for now. I think we've gotten something that resembles something reasonable. We will see. We'll have to play around with this after we fix this like unmap problem. We'll have to play around to see how much this actually works, right? But like it feels reasonable at least. It feels like we're going to get somewhere. So, I'm going to call it there for now. And we'll come back tomorrow once I've had some time to sleep on it. So, thanks for watching, guys. Hope you enjoyed. There's a YouTube link in the Twitch description if you want to see some other stuff. If you want to see like past streams or whatever, keep up. Otherwise, let's just find someone to raid.